In a previous video, I explained how to find the rate of a reaction. If you want to watch that, I'll put a link in the description below. However, I assumed throughout that discussion that the rate of the reaction was not affected by the concentration of the reagent. In this video, I'm going to look at a much more usual scenario, one where the concentration of the reagent does affect the rate. Here's the rate equation that we came up with last time. It allows us to calculate the rate based on the decrease in concentration of a reagent. If the rate isn't affected by the concentration, the rate is a constant, so let's give that the symbol K. If the rate is directly related to the concentration of the reagent, we can write a similar equation, which contains that concentration. In this case, K becomes the proportionality constant, the factor by which the concentration must be multiplied to get the rate. There is another possibility, which is that the reaction rate is affected by the square of the concentration of the reagent. So we can come up with another equation that describes that. These three equations describe the rate of the vast majority of chemical reactions. There are a few other possibilities, but these are rare and well beyond the scope of these videos. So, now we have three equations which can describe the rate of a reaction and its relationship to the concentration of the reagent. In fact, we can make these equations more like one another with a little mathematical manipulation. Our middle equation is correct, but we can make it look more like the last one by putting in a power to raise the concentration to. In this case, it's the power of 1. Anything raised to the power of 1 is itself, so this has no effect upon the numbers, but does make the equation look more like the final one. But what about our first equation, where the rate is not affected by the concentration at all? We can do the same thing here, but we multiply K by the concentration raised to the power of 0. Anything raised to the power of 0 is 1, and K multiplied by 1 is just K. So we've made this equation look like the other two without actually altering the maths at all. Now you may well say, what's the point of all this? Well, the point of this is that virtually all chemical kinetics can be described by one single equation where the concentration of the reagent is raised to some power which I've labelled n. N can be 0, 1 or 2 and is called the order of the reaction. We generally say that a reaction is 0th, first or second order. By the way, in all three cases, for a particular set of conditions, such as temperature, K will be a constant of the reaction, but different for different reactions. Since it's a constant which describes something about the rate, we call it the rate constant. So creative, us chemists. Yeah. So now we have three different types of reactions when it comes to describing the rate. Let's have a look at the effect of each of these types on the graph of concentration versus time. Here's the graph I showed last time. The rate is constant, and that is shown by a straight line graph. It has a constant gradient. This is the case for a 0th order reaction. If the rate is directly related to the concentration, as the reaction proceeds, the rate will decrease, and we end up with a graph like this. Notice that the gradient becomes less and less as time goes on, and the gradient at any point is our rate. For a second order reaction, the rate depends even more on the concentration of the reagent, and the curve is even steeper. However, we can still obtain the rate at any point by taking a tangent and calculating the gradient. Since our three different types of kinetics depend upon the power to which the concentration is raised, we can plot rate as a function of concentration to discover what type of kinetics may be going on in a particular reaction. Note that as we are plotting concentration of a reagent on the x-axis, as the reaction proceeds and the concentration decreases, we will move along the x-axis from right to left, not the other way around. So here are our three graphs for the different orders of reaction, and a set of axes for each of our rate versus concentration graphs. For the 0th order case, as the reaction proceeds, the concentration decreases, but the rate is constant, so we get a horizontal line as we move from right to left along the concentration axis. For the 1st order case, as the concentration decreases, so does the rate. The two are directly related to one another. So as we move along the concentration axis, the rate decreases in direct proportion, and we end up with a linear graph. For the 2nd order case, the rate is proportional to the concentration squared. So at the start of the reaction, the rate is high, but it quickly uses up the reagent and slows, creating a curved graph. Now, I hope at this point you have realized that there are a large number of reactions we haven't considered. Most reactions involve 2 or more reagents, not just one. What happens then? I'm so glad you asked. Here is a general chemical reaction. Again, I don't want to get involved in specific reactions, just general principles. This reaction has 2 reagents. Everything we have discussed so far applies to each of the reagents. This means that we have to be specific when talking about the kinetics of a reaction. Let's say that for this reaction the rate depends directly on the concentration of A, but on the concentration of B squared. We would say that the reaction is 1st order with respect to A, and 2nd order with respect to B. That phrase, with respect to, is very important. We can also report what is called the overall order for the reaction. We obtain this by adding up each of the orders. For this reaction, it's 1st order in one reagent, 2nd order in the other, so that the overall order is 1 plus 2. 3rd order overall. Of course, there are a variety of possibilities for the kinetics of a reaction between 2 compounds. Either of them could be 0, 1st or 2nd order, and hence the overall order could be 0, 1, 2, 3 or 4.